So we heard a lot about the Slim Bootloader today. We had already 3 talks that contained the Slim Bootloader. So pretty hot topic, right? Like I said yesterday, problem with documentation, technical documentation, is that it usually doesn't contain step-by-step guides. And today we have another step-by-step guide for porting the Slim Bootloader to actual hardware by these 2 folks. So please give a round of applause for Yawen and Jinju.
All right. So good morning, and I promise you this is the last presentation about Slim Bootloader before you get sick of us. All right, so my name, again, if you didn't attend the first topic this morning, my name is Yawen, and together with my colleague Jinju, we are going to share a practical guide of how do you port Slim Bootloader on your main board. That is reference from an Intel reference design. So we came all the way from Malaysia and to share this interesting talk with you. And we are from the Internet of Things group in Intel. So I'm going to go straight to the methodology of the mainboard porting steps, right? So in Intel, every time we come up with a new silicon or SoC, we will develop the silicon initialization code. Some will call it the silicon reference code, SRC. And it can be in the form of source code, and where we provide to the independent BIOS vendors or ecosystem partners. And also it can be in the form of the binary encapsulation known as the Intel FSP. Now, additionally, we will provide a firmware code to support for the Intel reference platform, namely the RVP or the CRB that's from Intel with the same SoC. So you got the code for the chip, you got the code for the mainboard reference design, and what does that mean to the customer? So OEMs generally will design a hardware, their platform based on our reference platform, typically the CRB, and make use of the reference Slim Bootloader implementation for your boot firmware development. So just 3 steps, very easy. So just now, my colleague Sheng, he shared the boot stages of Slim Bootloader. What does it do? So it looks pretty similar to how Coreboot does it. So typically, Slim Bootloader is separated into 2 parts. One is the hardware and silicon initialization phase, which will further break down into stage 1A, 1B, and of course stage 2. And the second is the OS boot logic payload portion. So from a very high level, let me describe what does the each different stage do. So in stage 1A is where you come up from the reset vector of the CPU. So it starts with some assembly code, and it performs some basic initialization, including setting up the car, provide some debug output. Now, in this stage is where we consume the first FSP binary block known as the FSPT before we hand over to the next stage, which is stage 1B. Now, in stage 1B, where code is written in C, we perform continue the rest of the silicon and platform initialization. Namely, very importantly, is the memory initialization. So this is where we get DRAM in it, and it's usually in the form of FSPM, where we have a platform, we have hooks to call into FSPM. At this stage, it also loads the configuration data. Now, I'm going to talk a little bit more on the configuration data, and I do have a demo later before we pass to stage 2. Stage 2 is where we have memory set up and ready to go. So stage 2, we perform the rest of the silicon init like FSPS. We set up tables like SMBIOS, ACPI, and we also perform the PCI enumeration. Now, with stage 1A, B, and of course stage 2 done, the hardware and silicon initialization is complete. And after that, we'll hand over to the payload. Now, in Slim Bootloader, we do provide a sort of like a EFI shell kind of like environment for you to do certain things, but the payload can be configurable. Now, Slim Bootloader, when you download from the repo, it comes by default. If you remember my first talk this morning, it comes default with the OS loader, and the second one is the firmware update payload. Now, the payload, what does it do is basically the logic to boot, to hunt for the operating system in the media, like a SATA hard disk, eMMC, and also then after that, you'll pass control. From then, the payload will pass control and load the operating system. So it's linear, it is predictable, and it consumes FSP. All right. So with that done, let's get started to port a Slim Bootloader for your main board. Imagine you have a mainboard and you're going to put Slim Bootloader. So these are the main, we sort of like summarize everything from a very high level perspective. And of course, you can go even deeper. We can have that conversation later. But from a high level, these are just a few steps that you need to do to port Slim Bootloader on the mainboard. Now, if you notice, I color coded this flow, the boxes and I'm not sure it's orange or yellow, maybe it's orange yellow. But for those two steps, those are optional steps. Okay, in case you need to perform more initialization, which my colleague Jinju will explain in detail later. So first things first, if you want to build something, you need to build up the system environment. Okay, so your system to build Slim Bootloader, we support building on both Windows and also Linux. Now in our in Intel, we have tried it with Windows, and the supported environment is you need to install Visual Studio 2015 or other versions which require the x86C or the C++ compiler tools. All right. And if you are building on Linux, like a question this morning from a gentleman, we have tested and tried to build it on Ubuntu Linux 18.04 long-term LTS, and also the compiler is GCC. Now the tools required to generate a Slim Bootloader binary are Python, ISL to generate ACPI images, NASM to compile the assembly codes, and lastly, OpenSSL. So you got the system set up. Now, where do you get the source? So my colleague Sheng earlier also showed where's the link to get the source. And if you go to this GitHub page, this is what you'll see. I take a snapshot of this just last week. I suppose it will be even more updated today. So click on the clone or download. That's where you copy the link, use git clone, and you get your source. And it's very fast. Why? This is what you get when you clone Slim Bootloader source. As you can see, it's pretty simple. That's what we are talking about this morning. It's small, simple, and highly flexible, as what is shared by my colleague Shen earlier on the previous topic. You can remove stuff and put in Linux boot and all that. So it's pretty simple. And the way it is structured also sort of like mimics the boot flow. As you can see, that's the stage 1A, 1B, 2 in the bootloader core packages. Now, just a very brief description of what they do. First is the buildloader.py. The buildloader Python script is actually the script that you invoke to build and generate the Slim Bootloader binary. That's the thing that you see here. So base tools is we leverage some of the tools from the EDK2 build. So we leverage highly from them. We don't recreate the same tools. Bootloader common packages is where we have libraries that is shared between the Slim Bootloader core and the payload. Now, bootloader core package is where we have the Slim Bootloader core files. And FSP2 packages is where we have files that is needed to tie in the FSP binaries and provide the APIs to call into that. MDE package is familiar if you are with EDK2. Now, payload package is where our OS loader and firmware updates are and anything related to that. Now, platform is where most of you will be doing your work in. So in this talk, because we're focusing more on mainboard, not silicon initialization, because Intel does the silicon initialization and you work on the platform. So you will be working mostly on the platform folder for those board-specific libraries. Now, the reason why it's libraries, because in the boot flow, Slim Bootloader will have that predictable linear boot flow, and it calls into the different platform packages in the form of libraries. All right. Lastly, silicon-specific libraries is located in the silicon package folder. Oh, that's a typo. That should be silicon PKG. So if you download this, you'll notice that whatever Intel has upstream into Slim Bootloader open source is really available. Today, we have Apollo Lake board, Coffee Lake, and QEMU as well. And of course, as what Ravi shared this morning, we will continue to upstream more support for the newer SoC as time goes by. So with that, I'm going to pass the time to Jinju, who will share with you the step-by-step to port your mainboard.
Okay, thanks, Yavan. Okay, so after you clone the source code, you get a source code, you can proceed to the location, the board config Python structure. And this file provides the board-specific static configuration, for example, the platform and feature configuration, the image layout information, and library instance, and the version information. Okay. And so this is the example content of the board config Python structure. And the upper part is the platform version information. And this is the part for the silicon feature configuration. And the lower part is for the platform features. And from what the previous my colleague Lenshin present, and you can add the Linux boot on the region there. And for example, you don't need the measure boot, you can set the measure boot value to 0. Okay, next, you have to assign a platform ID. Okay, so each board need to have an unique ID, and during the board porting, this ID is specified in the configuration delta file for the board. Okay, so during the boot process, Slim Bootloader will detect the platform ID and select a configuration data file and apply it to the board. So Slim Bootloader support up to 32 platform ID, but the ID 0 is reserved for the base reference configuration, and a single Slim Bootloader binary can support up to 31 board, 33. Okay, so next you have to create a platform configuration delta file. So Slim Bootloader comes with a graphic-based configure editor tools to let you to modify the settings such as the memory, GPIO, PCIe port from a base configuration. So by proceeding to the path, you can access to the config editor Python structure and use the tool to load an existing reference board delta file. And you update the platform ID for the board. And you can make any necessary changes to reflect for your mainboard configuration and save it to the new board delta file. And lastly, you have to include the new delta file entry in a board config Python structure. Okay, so now Yawen is going to do the demo for the config editor tool.
So as you can see from the previous slide, it's very wordy, I can understand, but nothing beats a demo, right? So I'm gonna show a demo. Okay, so the config editor tools is located in the bootloader core package in another subfolder called tool. So typically you just use Python to invoke it. Oh, it's in this screen. So let me pull it over. Where did my cursor go? There it is. So it will launch this. Let me maximize this. So the first thing you do is to load and open config DSC file. So in this example, we were using Coffee Lake, right? So let me go to the Coffee Lake folder. Platform, Coffee Lake, config data. There you go. So this will load the basic configuration that's available on the Coffee Lake reference platform. As you can see, there's a lot of, not a lot, but there are categories of the settings that you can go to. So the next step that we want to do, remember Ravi showed you that we have already added support for the Aeon up extreme board. So let's just load its configuration here. So load config changes from delta file. Do you want to continue? Yes, I'm very sure. So there we go, up extreme is right here. And you apply those config delta on top of this base configuration. So as you can see, if you click on, if you maximize it, under platforms, you can already start configure a lot of things like the boot device instance. Now remember about board ID. So you need to assign a unique board ID for your config delta file so that as Slim Bootloader boots, it will know which configuration that it needs to load and apply the settings to. All right. So for in this case, for the up extreme, we have assigned board ID 16 to it. Now, other than that, you can also give a name for your platform name, which is used, and the device type, hardware partition. So you can see there's actually quite a lot of settings in just platform alone. And ACPI, you can choose to disable, enable. Now, even though you can also disable some of the features in the board config.python structure, you can also do it in this config editor tool by enabling and disabling stuff. So a lot of this stuff is, we abstract all the source code, you know, like in my experience as a BIOS engineer, when we try to find certain settings, we do something called source code archaeology. We need to dig in and where's that setting? Is this a correct file? Does this file even build? So we abstract all that complexity and put it in a very nice graphical user interface for the modern engineer like me. So, okay, let's go to memory. As you can see, for the upstream board, it is with a, what do you call that? A memory down design, so that you don't actually have to plug in DIMMs. So where does the SPD configuration came from? You can even specify it here. So what we did is that we read the SPD from the BIOS and we just put it here. If it has any memory parameters that you want to change and pass into FSPM, you can do it right here. All right. So let's go to Silicon. So for the Coffee Lake reference platform, we do have an embedded controller on board. We can choose to disable it. It's disabled by default here. And also some other features like processor debug features, legacy serial I/O port, and so on. Now, some of you may have some PCIe configuration. So this is what is available on Coffee Lake. Let's take, for example, RP8. So these are all the PCI Express configuration that you can just click on the pull down menu, choose whatever you want. All right. So let me see what other nice settings that we can look at. Okay, let's collapse this. Payload, right? And also graphics. So graphics, like a GOP driver, there are certain parameters that you can pass into: the size of the pre-allocated memory, the aperture, whether you want to enable the EDP or HDP and things like that. And of course, there's general settings and everybody's favorite, GPIO. So we had a very interesting conversation yesterday during the break that, for an Intel SoC, GPIO initialization and configuration used to be a very simple process. Some base offset plus some other offset, enable, disable, you're done. But today, there are, correct me if I'm wrong, 4 dwords for each pad. And sometimes, and most of the time, we don't even know what the dword do. So it's very confusing nowadays. But with this config editor tool, it is now very easy to just configure your GPIO. And if you have the Intel EDS specification to know, okay, what does this pin's native function do and all that, it's all reflected here. All right. So bear in mind, up until now, we haven't looked at a single line of source code. Right. So OS boot options, we have 3 boot options. It's either from USB, SATA, eMMC in a particular order where you can swap around. And lastly, security for those who have security. In Coffee Lake, we have the feature of platform security discovery, if I'm not, PSD, and also software guard extension. So as you can see, let me do an exercise. Let's say my favorite, GPIO. I want GPIO A0. I want to skip it. And direction is an output when it's high. Okay, so these are all the changes I need to make for my Coffee Lake, own Coffee Lake board that's based on an Intel reference design. So after I make those changes, I will just save the config to a new Delta file. So keep it within this same folder. Maybe I'll just call it, where is it? Okay, so this is called up square. I'll just rename this OSFC board. All right, save it. Okay, so once you're saved, remember in the steps that Jinju outlined earlier, we need to, okay, let me go to this config. Oh, sorry. So I'm just going to load the board config.py file. Okay. So this is the board config.py file as what Jinju showed you earlier. Oh, I didn't see. So these are some of the settings that you can actually review. So the first step is just review this file. If there's anything you need to change or tweak, you can do it here. So I've got my new board, right? So where do I put it? Where do I tell Slim Bootloader that, please include my Delta file? So where did it go? Oh, it's up there. Up some more. Up. There. Okay, just slightly lower. It's hard to see this. Let's see. Oh, okay, there we are. All right. So as you can see, by default, it comes already with the three or four Delta files. So this is where you add your new generated file, config, data, and so on and so forth, whatever the new file that you just saved. All right. So that's basically all you need to do for your configuration and editing of all the settings for your platform and silicon. So I'm just gonna go back to the presentation, and Jinju will take it over again.
Okay. So ideally, the configuration can be done by using the config editor tool, but there is a cases where the board specific POTI is needed. So you can done it in the board support library. And for example, the serial console debug port, you need to configure to match the hardware configuration. And you can do that by using the external legacy UART device. So for example, the Super I/O chip and embedded controller. Or you can use the Internet SoC MMIO based UART. Okay, so you can modify the board specific SCPI table if needed, and this step is the optional step. So first, you can modify the DSDT if required, and for any additional SCPI table, you can create and paste them within the SCPI table folder. And lastly, update the SCPI table INF file to include the new entry. Okay, all right. The Slim Bootloader support, by default, it supports the OS loader that can boot with the Linux, ELF, multi-boot, for example, the Android and hypervisor, and PE image. So if you want to boot with the UEFI payload, so you have to clone the payload from the link, the GitHub channel called EDK2, and build it. And in the Mainboard Delta file, you can change the payload ID to UEFI. And lastly, you build it with the command stated. Okay, so lastly, to build, stitch, and fresh process. So firstly, you build the Slim Bootloader with the command build loader, build, and your platform name. So the build binary will be stored in the output folder, and together with a Slim Bootloader binary file, which is required for the stitching process. Okay, so for stitching, firstly, you have to get a full IFI image from either you can get it from Intel or you can read it from your board that contain the additional firmware ingredient. And you can stitch it with the command stated here. And lastly, you can flash the generated IFI image to the target board, to your target board, and the basic porting for your mainboard is done. Okay. So
yeah, that's basically all you need to do to get started to port Slim Bootloader on your board design that's based on an Intel reference. You got an Intel reference board, you get the schematics from an Intel representative, you design, you make your own hardware changes. Now all you need to do is to mirror that same changes into Slim Bootloader by using the config editor tool, save it and generate it, and then lastly stitch it, and of course don't forget to flash it. Now Intel, we do commit to keep our project documentation up to date and as detailed as possible. We actually receive feedback that the documentation is very good. But it is our responsibility to keep this documentation as updated as possible. And because this is a community project, we do encourage all of you to try it out, or at least go through the documentation and start posting questions and giving us feedback on how can we make it better. There may be use cases that we haven't thought of yet, like for example, what Ravi mentioned about Slim Bootloader reading UEFI variables from the UEFI payload. So that is actually very good feedback that we take it and internalize it, and then we implement that feature into Slim Bootloader, which is available today. So I guess with that ends our presentation slightly earlier.
Thank you, Xiaowen and Jinju. Please have another round of applause.
So feel free to ask us any questions, and we'll be glad to answer you. And I didn't do this earlier in my earlier topic, but the creators of Slim Bootloader are here, Ravi and Maurice. So feel free to engage with a meaningful discussion with them. Give them a hard time, please.
Here we have about 12 minutes for questions,
right.
So that should work. So again, feel free to go to the microphones and just ask your question.
MESM not available. Please set MESM prefix.
Sorry, I don't get it.
That's what I get when I try and build it. What is MASM? MASM.
MASM, that's an assembler, right?
Okay.
NASM.
Yeah, as an assembler to compile assembly language.
Yeah.
Okay.
We don't use MASM. NASM.
Oh, it's an N for nanny?
N, yeah.
Okay.
Yeah.
So I need to get that. I can't use GCC?
With
Yeah, so for cross compilation across the board.
You use NASM on Linux. Okay.
Just to confirm my understanding, OpenSSL is used just for creating signatures, but inside your actual binary, you're not including OpenSSL. You're using an Intel crypto library that's much slimmer. Part of that is because you don't do cert chaining. It's part of the verification process,
that is correct.
which is fine for some scenarios. So,
Yeah.
okay. So I wanted to mention that OpenSSL is a non-trivial size piece of how we do things in UEFI typically.
We understand that. Yes, that's true. All right. Seems like a pretty easy crowd.
There's still some time for questions, so
We'll hang around. No.
okay. But
Okay.
that seems to be it for now. Please have another round of applause.
Thank you.
Thank you, man.
Thank you.
Thank you very much.